In this video, we will look at examples of integration by parts. So we'll start with example 1, where we want to integrate x multiplied by e to the x. And what integration by parts tells us is it tells us a formula on how we can integrate u dv. So first things first, we're going to need to look at what we have in our integral and match up certain parts of that with u and match up certain parts of that with dv. And we get to make that decision on which part of our integral will be u and which part of our integral will be dv. So we will make a choice for u and we will make a choice for dv. I will make sure that when I choose my dv that I do include this dx in it. But to help us decide which one's going to be which, we're going to use the acronym LIGHT. And that L stands for logarithmic, the I stands for inverse trig, the A stands for algebraic, the T stands for trig, and the E stands for exponential. So when I go through this list, I'm using this to help me choose u. So right now we're talking about what are we going to choose as u. Well, there is no logarithmic expression in this integral, so I'm not going to choose a log. There is no inverse trig expression in this integral, so we won't choose that. Algebraic, there is an algebraic expression. Algebraic is simply the x. So for u, I will choose u to be x. That leaves e to the x dx on the inside of the integral. I will choose all of that to be my dv. So far we have rewritten our integral so that it is the integral of u multiplied by dv. Now the formula up here for integration by parts tells us that this integral is equal to u times v minus the integral of v du. That means that there's a few things we're going to need. We have u and we have dv, but what we do not have is we do not have du and we do not have v. So in order to get du from dx, in order to get du from u, we're going to take a derivative. Derivative of x is simply dx, or 1 dx. On the other side, we have dv, but we need to find v. In order to get v, we're going to have to integrate. So I'm going to take the integral of dv in order to get v. So I integrate dv, which means I'm integrating e to the x dx, and the integral of e to the x is e to the x. And I'm not going to put the plus c on this because I'm going to plug into this entire formula here, and I will put a plus c on the end after I plug into that formula. So recapping so far, we used this acronym to help us choose u. Once we chose u, everything else that was left in the integral was our dv. We then took the derivative on one side to get du and the integral on the other side to get v, and now we're about to plug into this formula. So we have u multiplied by v. U is x. V is e to the x. From that, we are subtracting the integral of v du. V is e to the x. Du is dx. So now we started with an integral of x e to the x, which we do not know how to integrate. We could not have integrated that with u sub. We do not know an integration rule for how to integrate that. And we've used this formula that's given us this new expression where we only have the integral of e to the x. Well, we know the integral of e to the x. It is e to the x plus c. And here is our final answer. So the premise of integration by parts is you take an integral that you do not necessarily know how to integrate, because we do not know how to integrate e to the x dx, and you break it up into parts. We have one part here that's already integrated, and we have another part here that's not integrated. And hopefully, if you do it correctly and you make a good choice for you by using this acronym, then this you should be able to integrate. most of the time. It may be that we'll see examples where we have to use integration by parts a few times. We'll see some examples where we have to do a little bit of algebra, but the whole point is that we take an integral that is complicated and we break it down into parts that are easier for us to work with. Moving on to example 2, we are again using the fact that the integral of u dv is equal to u times v minus the integral of v du. We have to choose u and we have to choose dv. I choose them from the inside of my integral. I always choose u first, and I choose u using LIATE. The L stands for logarithm. Is there any logarithmic expression in here? There is. So I'm going to choose u to be that logarithmic expression of ln x. That means that dv is everything else that is left in the integral. It is the x squared dx. In order to use this formula, we're going to need to take the derivative of u to get du. The derivative of natural log x is 1 over x, and I will put a dx on the end of that. And I'm going to need to take the integral of dv in order to get v. So when I integrate x squared, I get x cubed over 3. So now let's go plug into this integral. So we have u multiplied by v. U is natural log x, and that's being multiplied by x cubed over 3. I'm going to write the x cubed over 3 in the front. From that, we subtract the integral of v du. V is x cubed over 3, and du is 1 over x dx. I'll do a little bit of algebra here to simplify that second integral. Now that's something that can easily be integrated simply using the power rule. We are left with x to the third over 3. And then finally, I will simplify this answer, leaving us with our final answer here. Here in example 3, we are again going to use the fact that the integral of u dv is equal to u times v minus the integral of v du. We're trying to fill this out, so we need to come over here and pick u and pick dv. I choose u typically according to LIATE. L is for logarithm. Is there any logarithmic expression in the integral? There is. Natural log x. dv is everything else that's left in the integral. It is going to be just the dx. dv is always going to have the dx on it. It may or may not have other pieces with it. It just depends on what you chose to be your u and what was in the integral. Now, in order to use this formula, we need du. So I'll take the derivative of u, and I'll take v. So I'll take the integral of dx to get x. And one thing I want to point out that I haven't really mentioned yet in this lecture is notice that the integral of natural log x dx, we do not know how to integrate that. We do not have an integral rule for how to integrate natural log of x. You may be thinking that we do have an integral rule for 1 over x dx, which is natural log. We know how to take the derivative of natural log x, but we do not have a rule for how to integrate natural log of x. So this integration by parts section, a lot of the times we'll use this when we come across an expression that we do not know how to integrate. So we spent time in 8.1 talking about basic integration rules. They're not so basic, but the point is, at this point in your calculus career, you've built knowledge of integration rules. We will use integration by parts if we come across something that says, hey, we do nothing in our toolbox. We don't have any rule to integrate this. Integration by parts is when that can be used. Okay, so let's go ahead and apply this. We have u multiplied by v. U is natural log x. V is x. So I take x, multiply it by natural log x. From that, I subtract the integral of v du. V is x, and du is 1 over x dx. Simplifying what's on the inside of this integral, those x's cancel, and I'm just left with the integral of dx, which is simply x. Example 4, we're going to again be using integration by parts. I need to choose u and I need to choose dv. So take a second and look at this expression and think about choosing u. Which of the first of these show up? Is it a logarithmic expression? Is it an inverse trig expression, an algebraic, trig, or exponential? It is an inverse trig expression. Arcsine is an inverse trig expression. So that will be our u, which means dv will be everything else that was on the inside of the integral, which was just dx. We take the derivative of u. The derivative of arcsine is 1 over the square root of 1 minus x squared. And I put a dx on that. And we take the integral of dx to get x. So now let's go fill this out. So we have u multiplied by v, which is x multiplied by arcsine of x. We will be evaluating this from 0 to 1 because we do have limits on this integral. And from that, so this has already been integrated, right? So here I just have the fundamental theorem of calculus that will be applied. When I put my integral in, I'm still going to have these limits on it. Inside the integral, we have v du. That is x multiplied by this fraction here. So I'll multiply the x by the 1 in the top. The dx stays on the end. And I have 1 minus x squared in the denominator under the square root. Remember, the whole purpose is that hopefully this integral here is something that we do know how to integrate, and we do. We can easily integrate that using simply a u sub. Choose u to be the expression in the denominator. There's our du. I don't need the negative 1/2, so I'll divide both sides by it. My integral would become u is in the denominator under the square root. Now we will increase our exponent by 1 and divide by our new exponent. And we are left with a negative u to the 1/2 plus c. In this case, u was 1 minus x squared. So now let's go plug that back into what we have. Still need to evaluate this from 0 to 1, but we just saw that this integral here is equal to the negative square root of 1 minus x squared. I put the plus c down here when I integrated because I did this u sub with no limits. But now that I'm back into the problem where there is limits, I'm just going to put that all of this needs to be evaluated from 0 to 1. So I'm just changing my notation. I'm going to show that I'm going to evaluate all of that. Do be careful with your signs here because there is a minus sign built into the integration by parts formula. And we have a minus sign that we picked up through our integration. So it will ultimately end up being a plus sign. So now we're ready to apply the fundamental theorem of calculus. First, we'll plug in our upper limit of 1. Then we'll subtract and plug in our lower limit of 0. The whole first term will go to 0 because of that 0 there, that x right there. So let's see what we have. We have 1 multiplied by arcsine of 1. Arcsine of 1 is pi over 2. Thinking about where is the y-coordinate 1 on the unit circle between negative pi over 2 and pi over 2. Plus this will be 0, 0, and that'll be 1. So we are left with a final answer of pi over 2 minus 1. I begin with thinking of how I want to choose my u. There's no logarithmic expression, there's no inverse trig expression, but there is an algebraic expression, it's x squared. So dv will be everything else that's in the integral, sine x dx. To get du, we will take the derivative of u, And to get v, we will take the integral of dv. Now we'll come and plug into the formula. We have u multiplied by v. And from that, we subtract the integral of v du. Do notice that v is negative, so we will end up with a plus sign. So we're left with an integral with x cosine x on the inside. I am going to I'm going to change the way I write this, and I'm going to choose to write that 2 there, and I'll say why in a second, because the fact of the matter is we don't know how to integrate x multiplied by cosine. If it were just cosine, we could integrate it. If it were just x, we could integrate it. If it were a plus sign in between, then we could integrate it. But with this multiplication in between, we cannot integrate. And so we are going to have to use integration by parts on just this integral here, which is why I pushed the 2 on the inside, because when I go to choose u, thinking about LIATE, there's no log, there's no inverse trig, but the A algebraic is 2x. So my du would be 2 dx. V is everything that we did not choose in the integral, so it is cosine x dx. And so our v is positive sine x. And on this part here, I'll bring this straight down. But on this part here in blue, for this integral, we're going to have uv minus the integral of v du using these values here. So u times v is 2x sine x minus the integral of v du. V in this case is sine x. Du is 2 dx. So we have 2 sine x dx, and this is something that we do know how to integrate. So we had to use integration by parts twice. We did have to use it twice because the x started off squared in the problem. But now we have an integral that we do know how to integrate. Because we know that the integral of sine is negative cosine. So the negative and that minus sign in front will combine to a positive 2 cosine x. And then we will add our constant of integration, c, and have our final answer.